Hi everyone, this is week 14 Q&A where we cover the questions that you asked about chapter 18. I really like this first question. This one was asked by Quaid. Are all processes reversible, similar to how every chemical reaction is reversible? Now the reason why I like this question so much is because it's actually a deep philosophical question that is much more difficult to settle and understand than you might think at first glance. Interestingly, the major microscopic laws that describe physics are all reversible. So those include Newton's equations, Schrodinger's equation. It's also reversible. That is the main equation that we use in quantum mechanics. And by the way, the more advanced form of the Schrodinger's equation is the Dirac equation, also reversible. And then lastly, Maxwell's equations, which describe the motion of light, electromagnetic waves, etc., all reversible. So then is the answer to your question yes? Not exactly, because what is something that we directly experience that does not seem to be reversible? That's the passage of time. The fact that time seems to only go in one direction actually caused people a lot of confusion for a long time. It seems to be a paradox. Time seems to only go in one direction, and yet all of these equations are reversible. So what causes the so-called time's arrow? What causes time to seem to be irreversible? And that's a very difficult question to answer. I don't think I know of anyone who explicitly knows the answer to that question, though some people have some ideas for why this could be. And it's possible that one reason for time's arrow is the second law. Now, if you recall the second law, at least in its popular form, says that entropy of the universe always either stays steady or increases. And that actually offers a potential explanation for time's arrow. It's possible that there is a thermodynamic explanation for time's arrow. And here's the reason: that the systems will spontaneously move towards maximum entropy. And that a way of thinking about that is they're moving towards equilibrium. And the universe itself is out of equilibrium. And so that's why time is moving in one direction in order to restore the universe to a state of equilibrium. Or maybe not restore it, but bring it to a state of equilibrium. It's a very mysterious issue. And it's one that scientists don't fully understand quite yet, though maybe we will someday. All right, the next question was asked by Jeffrey, and I'm paraphrasing here, but he asks, are both thermodynamic and kinetic approaches taken when doing drug synthesis? Now, this is not necessarily my area of expertise. I don't know that much about synthesis, but I can tell you that from a medicinal chemistry perspective, as far as I studied, and especially when looking into drug efficacy, drug specificity, pharmacodynamics, pharmacokinetics, the answer is definitely yes. You definitely consider both thermodynamics and kinetics when evaluating the potential effectiveness of a drug for its therapeutic purpose. When it comes to synthesis, you definitely, like I said, I don't understand that much about it, but if the drug takes too long to synthesize, that's a kinetic concern. And if the synthesis pathway is thermodynamically unfavorable, then you're not going to be able to synthesize it. So I would strongly suspect, yes, that for synthesis, you need to consider both thermodynamics and kinetics. All right, the next question was asked by Adam. Can you use the stoichiometric coefficients to get both the equilibrium constant and the rate law? And the answer is yes for the equilibrium constant And the answer is no for the rate law. You cannot use the stoichiometric coefficients of the overall reaction in order to find the exponents for the rate law. So what do you do instead? You use the stoichiometric coefficients from the slowest reaction mechanism step. So if you know the reaction mechanism and all its steps, you could find the slowest step, use those stoichiometric coefficients, and that will give you the rate law. The next question was asked by Cece, and she asked, for the different methods of finding the rate laws, is one more common than the others or more accurate? And I'm not really an expert in this because I'm not an experimentalist, I'm a theorist, but as far as I understand it, the method of initial rates is the most common way of doing it. Though it may not work ideally for every circumstance, and I'm sure that in certain situations, a different method may yield more desirable results, maybe more accurate, maybe more quickly, etc. Okay, the next question was asked by Madison Malone, where she told me that in day 1, video 3, around minute 3:58, I said that there was a rate law that was first order in a couple of reactions. So let's actually take a look back at this particular reaction. What I said was that A plus B plus C goes to products. So as you can see, this is an overall reaction. But then, in addition to that, I gave some mechanism steps. So first, A combines with B to form the complex AB. Then AB combines with C to form the products. And I said these were mechanism steps. And this was the slow step, and this was the fast step. And I said that we could construct the rate law by looking at the stoichiometric coefficients for this step of the mechanism. Notice you cannot use the stoichiometric coefficients of the overall reaction to get the rate law. It won't work. You have to use the stoichiometric coefficients of the slowest step, if you know the mechanism, in order to construct the rate law. So the rate law in this particular case was K, concentration of A, concentration of B. And C doesn't even appear in this expression because it's part of the fast step, and A and B have a stoichiometric coefficient of 1, so therefore they're rate order 1. So I'll just put those 1s up there to be even more clear about that. Okay, the next question was asked by Josh, and I like this question. I'm really paraphrasing him here, but he says, essentially, if we can draw a direct relationship between thermo and kinetics, how can we increase the forward rate without changing the stability of the products or the reactants? I really think the best way to think about this is, again, to use one of these landscapes where we have a barrier to the reaction. So here's our double dagger transition state there. Over here we have the reactants, and down here we have the products. Now, if we change the location of, say, the favorability, say, of the products, I'm not sure exactly how we would do that. I don't know, maybe through changing temperature or changing pressure, then you would actually be increasing the backwards rate. So if we have a reversible reaction here, yes, by increasing the favorability of the products, you would be increasing the backwards rate without increasing the forward rate. But it is also possible to increase the rate without changing the favorability of the products and reactants. So let me just redraw my curve here. If you, say, lower the barrier, like using a catalyst or something, then you have increased the forward rate without increasing the stability of the products or the reactants. The thing is you have proportionately increased the backwards rate too. So you can't change the rate, you can't change the rate constants without changing the rate constants going in the other direction, or without changing the stability of the products or reactants. Something has to change if you're changing one of those rate constants.